This is a continuation of the previous video, post midterm weeks 5 to 10. So let's get right into it. So the quizzes consist of OSPF E3, OSPF troubleshooting, and then we have ACLs, and then NAT for quiz 8. However, what was not included was the next slide on VPN and IPsec. So let's get right into it. So this is a slide deck, single and multi-area OSPF config and T-shoots. So troubleshoot. Single area OSPF v3. OSPF v3 exchanges IPv6 prefixes and builds a IPv6 routing table with IPv6 prefixes. OSPF v3 builds three OSPF tables, of which is the neighbor table, topology table, and a routing table, of which neighbor table consists of an adjacency database, topology table consists of a link state database, routing table consists of a forwarding database. OSPF v3 runs independently, exclusively for IPv6 networks. OSPF v2 runs independently of OSPF v3, exclusively for IPv4. OSPF v3 runs independently only for IPv6. Similarities between OSPF v2 and OSPF v3. So, similarities include they are both a link state routing protocol. Both utilize the routing algorithm utilizing shortest path first, SPF. Metric is based on cost and bandwidth. Areas utilizes areas, uses and supports two-level hierarchy with areas connecting to area 0. Packet types, so OSPF packets, hello, DBD, LSR, LSU, LSA, LSAC. Oh, oops. Okay. So neighbor discovery, OSPF states, transition through states using hello packets, dr/bdr election function and process. Router ID are both 32-bit despite OSPF v3 utilizing IPv6. Remember this. Okay, so differences between OSPF v2 and OSPF v3. Advertisements. So this is done through IPv4 network addresses and the IPv6 addresses prefix. Source address, so IPv4 source address, and then the IPv6 link local address. Destination address, so IPv4 choice of neighbor, IPv4 unicast address. So remember 224.0.0.5 is a multicast address for all OSPF v2 routers. 224.0.0.6 multicast address is for dr/bdr. So basically for communicating only to those people. IPv6 has a choice of link local address. FF02:5 is a multicast address for all OSPF v3 routers, and then 6, so I think it's similar to the IPv4. So FF02 :6 multicast address dr/bdr communication to them. So advertising networks, IPv4 command. This is done through config dash router and then network and then router there. This was not compiled properly, so just ignore this. And then you advertise it. So you advertise networks with network address and then the address you'd like to, the interface you'd like to, and then choosing which type, of which we covered in weeks 1 to 4. And then IPv6 command here. So IPv6 OSPF process ID. So PID, so it is shared between all within OSPF and the area, and then the area ID. So let's control I here. So yep, that's how it is, and you could do this for a range of which is quite simple. I remember. So IP unicast routing. So IP unicast routing is enabled by default. However, for IPv6, it must be enabled. So therefore, you go in IPv6 unicast dash routing. And then authentication wise, IPv4 is plain text and MD5. And then for IPv6, it is IPv6 authentication or IPsec. So link local addresses, IPv6 link local address. enables device to communicate to other IPv6 enabled devices on the same link, and only on that link subnet. Therefore, packets with a source or destination link local address cannot be routed beyond that link. IPv6 link local address are used to exchange OSPF v3 routing protocol messages. So OSPF v3 network topology assign a link local and interface IP. So you do your IPv6 unicast routing, and then um, IPv6, and then instead of doing IP router OSPF and then your process ID for IPv6 is simply just add a v6 to it. So IPv6 and then doing your router ID here, and then setting up, um, yeah, you can manually configure it here or set it to the highest loopback or up and up interface. So there we go, and then here's how you configure a link local address. So assign a link local address to make it easier to manage and verify OSPF v3 configs. And then here's how you set up an IPv6 address, quite simple. And then here, IPv6 OSPF, and then your process ID, and area, and then the number. So this is how you enable OSPF v3 routing on an interface. So unlike IPv4, where you could, well, actually, it's the same way. You could just do IP, for IPv4, but for IPv6, same. You could. It's really simple. Really, that's what I'm trying to say. Really easy. You could do int range and then IPv6, process ID, and then your area and the area number, and then there you go. So it is easier to configure across all. And then this is how you verify. Show IPv6 interface brief. Note that if not configured manually, the IPv6 link local, it is generated using EUI64, the method seen in weeks 1 to 4. So an example of it being used. So default link local is FE80, but then the new one is FE80 double colon, and then the last 48 bits, no, last 64 bits are turned into last 48. Yeah. Oh, forgot how many bits, but you know what I mean. Yeah. Yeah, last 64 bits. Yeah, cause EUI 64. Yeah. So, sorry. Yeah, so it turns into a 64-bit address here in hexadecimal. So, from originating from the Mac using EUI 64. Okay, so modifying an OSPF v3 router ID. So overwrite the original. Note that after changing router ID, you must clear OSPF process to force renegotiations with the router ID. This should be noted for the previous section for setting up the router ID. You could do clear IP OSPF process. For IPv6, you just add a v6, and then you verify with show IPv6 protocols so that you can renegotiate a router ID. Now you verify OSPF v3 neighbors just like with IPv4, show IPv6 OSPF neighbor. So to verify neighbor connectivity, and here are the states here. It's quite simple. There we go. And then verify protocol settings. So with show IPv6 protocols, you can see the router ID, number of areas, so normal, stub, NSSA areas, and then you can see interface IDs. And then verify a specific OSPF v3 interface. So show IPv6 OSPF interface. So this is broad for all interfaces. And then you could do the extension of it with the specific interface there. And of which you could see the hello and dead intervals and more information. You could do brief to show easier output, of which is here. Now you could verify the routing table and OSPF v3 routes with show IPv6 route and show IPv6 route OSPF, of which you can see the states here. Here are some codes I may remember. So B equals BGP, R equals RIP, OSPF is O, and then remember O E1 O anything actually is OSPF. And then OSPF v2, v3, troubleshoot. Remember that network types, point to point. This is basically, again, troubleshooting steps for both v2 and v3 as they share functions there. So for point to point, this is two routers interconnected over a common link, no other routers on the link. Common configuration in WAN, you could see here. Uh, there we go. So broadcast multi-access network type. So this is multiple routers interconnected over an Ethernet network. So an Ethernet LAN. It looks like so. Non-broadcast multi-access NBMA. Multiple routers interconnected in a network that does not allow broadcast. The frame relay wide area network protocol is an example of an NBMA network. Now, what you're seeing here is not exactly covered within the midterm and therefore not seen in the final. So I'm just going through it because I can. Haha. So point to multi-point, multiple routers interconnected in a hub spoke topology over NVMe network, often used to connect branch sites, spokes, to a central site hub. And then virtual links, special OSPF network used to connect distant OSPF areas to the backbone area. Basically, uh, yeah, as it says there. Now the most important areas here, using OSPF states to troubleshoot. So establishing neighbor states adjacency. So remember the OSPF 7 states. So you have one down in it, and then two in it, three, the two-way. So these three steps here, down in it two-way, establish neighbor adjacencies. Extart exchange loading is synchronization of the OSPF database. And then 7 is the full state, complete synchronization. OSPF troubleshooting commands. It's quite um, self-explanatory. So we'll move on to ACLs. Fun. So module 4, access list concepts. 4.1 ACLs. What is their purpose? So what is an ACL? So not the leg thing. Okay. So is it like I don't know. Alright. So series of iOS commands that are used to filter packets based on information found in the packet header. By default, a router does not have any ACLs configured. So within ACLs contain ACEs, the access control entries, ACL statements, sequential list of permit or deny statements, compared to an interface configured using with an ACL, comparing the information within the packet against each ACE in sequential order to determine if it matches the process of packet filtering. So that's how they do it. So several tasks are performed by routers, require ACLs to identify traffic. So basically filter the traffic based on traffic type to give priority to certain classes. Screen hosts to permit or deny access to network services. So there are limited number of ACLs per interface. So 4 ACLs applied, 2 IPv4, 2 IPv6, consisting of outbound and inbound. So 1 outbound IPv4, 1 inbound IPv4, 1 inbound IPv6, 1 outbound IPv6. I hope I said inbound and outbound, but you get what I mean there. Okay, so ACLs do not have to be configured in both directions like a coffee filter, right? You don't want to do an inefficient way of filtering the process. So, ACL operation. Once applied, there are operational steps, 5 operational steps here. So, 1, the router extracts the source IPv4 address from packet header. 2, starts from the top of the ACL and compares the source IPv4 address to each access control entry in a sequential order. This is quite important. Basically checking, this is how it begins the filtering. Once a match has been made, third, the router carries out the instruction, either permitting or denying packet, and the remaining ACEs in the ACL if any are not analyzed. If the IPv4 address does not match any of the ACEs in the ACL, the packet is discarded because there is an implicit deny access control entry automatically applied to all ACLs. Keep in mind that. So that's why it is quite hard when configuring this. So then fifth, the final step, the last access control entry of an ACL is always an implicit deny that blocks all traffic. It is hidden and is not displayed in the configuration. Note that an ACL must at least have one permit statement, otherwise all traffic will be denied due to implicit denial. 4.2, wildcard mask in ACL. We already reviewed this, setting all network bits to off, setting all host bits to on. And then you could do wildcard mask types to match a specific host. So this is an example of permitting a single host IP. So access-list 10 permit 192.168.1.1 quad 0. Quad 0 only allows a single host IP. And then again here, this is another example. So might be wondering, what is this number here? This is a range of which we'll cover in the configuration of ACLs. So wildcard mask key host. So remember that there is a host and any. So you do this for a specific host address. So 0.0.0. So your address here. So we've seen this here. 192.168. Sorry, here. 192.168.0.0 for a specific host. And then for any, you could do for any address within a range. So basically an entire network. So basically this is the address here rather than for specific subnet. You do for all here. Forgot to mention here. You could permit or deny hosts within a subnet. So access-list and then forgot the number range, and then permit or deny here. And then your addresses that you'd like to do, make sure it's only the network address here. And then the wildcard mask here. Hey, 4.3 types of IPv4 ACLs. So we have standard ACLs and extended ACLs. So standard ACLs permit or deny packets based on only on the source IPv4. Extended ACLs, however, filter at layer 3 using source and or destination addresses, can filter at layer 4 using TCP or UDP ports, cannot filter based on MAC addresses. Rules in an extended ACL should be ordered most specific to most general. So where should we place our ACLs? This is quite important. Should be placed at the greatest impact on efficiency. Extended ACLs are located close to the source of the traffic to be filtered, whereas standard ACLs are located close to the destination to be filtered. So standard ACL placement example, so place it as it is coming into the network. So filter for coming in. So here we have the coffee filter here. We're filtering traffic coming from the 192.168.10 and only to this area here. So that is the coffee filter taking things, and then that is the filter down there. Extended ACL placement example. Say the source is from the PC. Place an ACL on the router of which the PC uses as a default gateway. So here, so filtering traffic from PC2. Okay, boom. And then another filter going to its default gateway here. So nice. That's how you did it. It's better to look at configuring because that is how we get to know to use ACLs, as it is quite easy to understand. So module 5, new slide deck, ACLs for IPv4 configuration. So numbered standard ACL. So note that numbered standard ACL is 1 to 99, so you could choose any there. Standard ACL. And then for extended is 1300 to 1999. Now, this is how you configure one. So access dash list, then your number, deny or permit, and then the source, and then source wildcard, and then log is this requires a separate video to give examples. So I'll just go through it quickly. And then you could do a name standard ACL. So this is another way of configuring ACL in ACE entries. So you could do IP access dash list standard and then ACL name. So creating the ACL name. And then now you're in a specific configuration terminal for the standard ACL name standard one. And then you just do your um, statements there. I'll look at my lab journal to better, because for these commands, it is best to look at it. So, and then to modify an ACL, you can use a text editor or use sequence of numbers. So method one of using a text editor, you just copy it into a text editor, make it necessary changes, and then remove the previously configured access list with no access list and then an access list number. Removes it from the running config, and then copy and paste it. And then method two, you could do it from the sequence of numbers. So here is it in action. So IP access dash list standard one, no 10, and then 10 deny host 192.168.10.10. And then there you go. Quite simple. Just removing a specific numbered entry here. There we go. So 5.3, secure V2Y port lines with a standard IPv4 ACL. So access class command. So this is how you perform that. This is done within the line configuration terminal. So access dash class. And then for our case, it was just access dash class in for our lab. And then configure extended ACLs, configure filter access list. So example permit and TCP and any protocol number or name. I hope I have my protocol numbers here. But yeah, it's quite simple. And then to verify, you show access lists. And you have to set, right. For extended IPv4 ACLs, when you're setting it up, you must configure for the interface and set its access group, whether it's coming in or out. Okay, so module 6, NAT for IPv4, 6.1 NAT characteristics. So IPv4 address space again. Just remember the private addresses. It is quite familiar. 10.0.0.0/8 is a private address. See this at home 172.68. 172.16.0.0/12 and 192.168.0.0/16. So this is private RFC 1918 networks. So NAT shields private addresses from the global internet. Translation of private addresses to public addresses. Yeah. So NAT for IPv4, this is just a review from last year again. But it's good to go through it again because you never know. What is NAT? Conserve IPv4, public IPv4 addresses. A stub network wanting to communicate to the internet uses a NAT-enabled network. So at home, this is what we use, right? And so converts your your private address to a publicly routable address. So in that terminology, it includes four types of addresses. So you have inside local, which is the private address, and then the inside global. This is two primarily used. So typically a IPv4 address, as listed here, and then consisting of public IP here. So um, inside local, yeah, private address. Inside global address is a translated public address. The address of the source as seen from the outside network. Outside local address, however, is a address of the destination as seen as from the outside network. And then outside global address is a address of the destination seen from inside its network. So here's an example of it in action. Yeah, it's quite simple. We could go through it. Okay. So from my PC1, my source address is my inside local address, and then my destination address is my outside local address. So here, so my packet 192.168.10.10, that is my source address, and then my destination address is 209.165.201.1, and then it reaches, that's what I'm trying to reach, the web server here. And then the source address here inside global, the destination of the seen from outside the network here. Then it swaps back there. Separate video. Okay, 6.2. Types of NAT. We have static NAT, one-to-one mapping of local and global addresses. This is manually configured by the network administrator, hence the static. Useful for web servers or devices that need to be consistent. Useful for devices that must be accessed by authorized personnel. Dynamic NAT is a pool of public addresses and assigns them based on a first come first served basis. The network inside network requests access to outside network. The dynamic NAT provides an available IPv4 address. Packets traveling outside to inside. Destination IP is translated. Packets traveling from inside to outside. Source IP is translated. Quite important here. So port address translation, known as PAT, also known as NAT overload, maps multiple private IPv4 addresses to a single public IPv4 address, or a couple public IPv4 addresses, depending on configuration. PAT, when receiving a packet from the client, use the source port number to uniquely identify the specific NAT translation. PAT ensures the devices use a different port, a TCP port for each session with a server on the internet. So again, imagine, I believe for some workplaces, using one public IP that is shared within a private network. Okay, so NAT key features comparison only modifies the IPv4 addresses, inside global address, inside local address. So one-to-one mapping between inside local and inside global addresses uses only IPv4 addresses in the translation process. A unique inside global address is required for each host accessing outside networks. PAT key features comparison modifies both the IPv4 address and port number. So inside global address, inside local address. So it adds a separate section here so it can remember who it's assigning things. So one inside global address can be mapped to multiple inside local addresses, uses IPv4 addresses and TCP or UDP source port numbers in translation process. A single unique inside global address that is shared allows hosts to access outside networks. So 6.3, NAT advantages and disadvantages. So NAT advantages, 1, conserves legally registered addresses by allowing the privatization of intranets. 2, increases flexibility of connections to the public network. hides the private IPv4 addresses of users and other devices. NAT disadvantages include end-to-end addressing is lost, end-to-end IPv4 traceability is lost. NAT also complicates the use of tunneling protocols such as IPsec, though, according to the lecture note, no longer the case. 6.4 Configure static NAT. So steps to configure, create a NAT mapping between the inside local address and the inside global address. So IP NAT inside source static, and then your private network, and then your public network to be translated, and then configuring um, the interfaces participating in the translation as inside or outside relative to the IP NAT inside and outside commands. So serial 0/1, 0 is IP NAT inside, and a separate interface is IP NAT outside. This is a reference to its topology. Oh, so verify static NAT, show IP NAT translations, or which shows active translations, and then show IP NAT statistics, which shows the total number of statistics. Now, 6.5, dynamic NAT. 5 steps to configure dynamic NAT. So define the pool of addresses that will be used for translation. So IP NAT pool, and then the name of the pool, IPs, then the starting IP to the end of that IP. Basically, arrange. Sorry. No. Alright. Net mask, and then the subnet mask there. So configure a standard ACL to permit only those addresses that are to be translated. So access dash list and your number, permit, and then that certain thing you'd like to permit or deny, whatever. You're just configuring an entry to permit. So bind the ACL to the pool using the IP NAT inside the source list. So IP NAT inside source list number and then pool name. So ACL number has to match between step 2 and 3. This is quite important. Step, do not forget. Fourth, identify which interfaces are inside. So IP NAT inside. Identify which interfaces are outside. IP NAT outside. So like what we saw before. Okay. So then you verify show IP NAT translations, show IP NAT statistics, and then you can clear IP NAT translation as by default translations clear after 24 hours, and it can be reconfigured using this command. Okay, pat. So NAT overload. To configure pat to use a single IP address, you use IP NAT inside source list. One interface gigabit 0/1 overload, and then you could configure pat to use a address pool, of which you do IP NAT inside source list one NAT pool. So this is the name. Overload. This is the number, ACL number. Yeah, the same troubleshooting steps. Best to see this within a lab setting, of which I'll do a separate video. Okay, which I'm probably lying. Haha. Okay, so module 8, the last one, VPN and IPsec concepts. So 8.1, VPN technology, virtual private network. Create end-to-end private network connections. Uses virtual connections that carry information within a private network, of which is transported over a public network. VPN traffic is encrypted, keeping privacy and confidentiality. VPN benefits include cost savings, security, and scalability, which makes sense. Modern VPNs now support encryption features such as IPsec and SSL. Two types of VPNs exist. So, first we have site-to-site VPN, aka LAN to LAN. Terminated on VPN gateways, VPN traffic is only encrypted between the gateways. Internal hosts have no knowledge that a VPN is being used. Remote access VPN is dynamically created, establishes a secure connection between a client and VPN terminating device. Simply a remote worker, for example, but needs to connect back to their private network, which is their office. Enterprise and service provider VPNs. VPNs can be managed and deployed as either enterprise managed VPNs or service provider VPNs. So enterprise VPNs, managed VPNs are a common solution for securing traffic, enterprise traffic across the internet. Site-to-site and remote access VPNs are created and managed using IPsec and SSL VPNs. Contain site-to-site and remote VPNs here. Now for service provider VPNs. They are created and managed by the service provider network using multi-protocol label switching (MPLS). MPLS at layer 2 or layer 3 to create secure channels between an enterprise's sites, effectively segregating the traffic from other customers' traffic. Does not provide encryption as it is a labeled switch path. 8.2 Types of VPNs. So remote access VPNs let remote and mobile users securely connect to the enterprise, typically enabled dynamically, and can be created with either IPsec or SSL. So as a clientless SSL connection, the connection is secured using a HTTPS SSL connection. Example given using a web browser, limited compared to client-based. Client-based VPN utilizes a VPN client software. Example given was Cisco AnyConnect Anywhere Access. Must be installed on the remote user's end device, able to access more resources as if they are within the office there. So SSL, Secure Sockets Layer VPNs, SSL/TLS is secure web browsing. HTTPS website users can be assured of confidentiality. So remember the three security concepts from last year: confidentiality, integrity, and authenticity. Basically, confidentiality, encryption between clients and servers; integrity, documents signed by the certificate have not been altered by in transit by a man in the middle, somebody looking at your files. Basically, making sure the integrity of the files are good. Authenticity, the server presenting the certificate is in possession of the private key that matches the public key in the certificate. SSL uses public key infrastructure and digital certificates to authenticate peers. It is a type of VPN based on the access requirements of the users and organization's IT processes. SSL gives access to the website browser or web application, not the entire network. All browsers have SSL built into them from the start. TLS has superseded SSL as it is more secure. Uh, TLS equals transport layer security. Side note, there are two ways of encrypting. We have asymmetric, which is what was I writing here? Authenticate to private to public based on certificate. Encryption to public to private. Massive takes a while for the CPU to encrypt and decrypt, whereas symmetric is based on a standard key and secret key. This was a side note from the professor, so not too in depth there. I think he just wanted us to just have a broader knowledge there. So, as best as we could before we get into cybersecurity. Okay, so site-to-site VPNs, site-to-site IPsec VPNs connect to networks across untrusted networks such as the internet, public networks, and hosts and receive send send and receive normal encrypted TCP/IP traffic through a VPN gateway. Routers and firewalls are doing the encryption for us. Well, that's good. So, notable IPsec versus SSL VPNs. There are some notable differences. But essentially, from here, IPsec is more strong in the fact that it gives more stronger services in authentication, encryption strength, and connection complexity, and yeah. Service provider MPLS VPNs. Today, service providers use MPLS in their core network. Traffic is forwarded through the MPLS backbone using labels. Traffic is secure because service provider customers cannot see each other's traffic. MPLS can provide clients with managed VPN solutions. Securing traffic. Essentially, securing traffic between client sites is the responsibility of the service provider. There are two types of MPLS VPN solutions provided by, excuse me, supported by service providers. We have layer 3 and layer 2 MPLS VPNs. Layer 3 looks at route peering with some protocol, OSPF or EIGRP, forming router adjacency. Layer 2 MPLS VPN, forming router adjacency between your two sites. A layer 2 connection, effectively like you're being on the same multi-access network. IP3, IP, oh my gosh, 8.3 IPsec. So IPsec technologies. So what is IPsec? It is an IETF standard that defines how a VPN can be secured across IP networks, protects and authenticates IP packets between a source and destination, providing essential security functions. So essential security functions include um, the usual CIA, so confidentiality, integrity, authorization, and then the last being DH, Diffie-Hellman. So let's start confidentiality through encryption algorithms, preventing threat actors from reading packet content. Integrity, using hashing algorithms, ensures packets have not been altered in transmission. And then we have authorization, using Internet Key Exchange, IKE protocol, to authenticate source and destination. Um, yeah, IKE performs authentication between two endpoints to establish security associations, SAs, aka IKE tunnels, used to carry control plane and data plane traffic for IPsec. IKE tunnels are unidirectional, therefore one way, so must have one going outbound or inbound. Okay, so then fourth, so CIA, DH, secure key exchange. Fourth is secure key exchange using Diffie-Hellman, uses asymmetric key exchange, so algorithm for key exchange. DH, so Diffie-Hellman, is a public key exchange that allows two IPsec peers to establish a shared secret key over an insecure channel, such as the internet. Okay, so IPsec additional information. They are not bound to any specific rules for secure communications. They may easily integrate new security technologies without updating existing IPsec standards. The open slots in the IPsec framework can be filled with any of the choices below. So IPsec framework, so IPsec protocol here. So we have yeah, so this is framework here. I think I've referenced it throughout. So here, IPsec encapsulates packets using authentication header, AH, or encapsulation protocol, security protocol, ESP. So AH is when confidentiality is not required or permitted. So remember, authentication header is when confidentiality. Oh, it seems against what the authentication header is about, because apparently it lacks authentication, whereas encapsulation security protocol (ESP) provides both confidentiality and authentication. And then for the confidentiality bit, we have it's essentially the degree of confidentiality depends on the encryption algorithm and the length of key used. The number of possibilities used um, um, to hack the key basically. The shorter the key, the easier it is to break. Below are the following encryption algorithms highlighted in the figure, of which are all symmetric key systems. So DES, which is a 56-bit key, 3DES is three independent 56-bit encryption keys per 64-bit block. I doubt this will be on the quiz. Oh no, on the final, but let's keep going. AES offers three different key lengths: 128 bits, 192 bits, 256 bits, and then Seal, 160-bit key, Stream Cipher, which essentially encrypts data continuously rather than just encrypting blocks of data. So there we go. That's a diagram here. Next, we're on to the next part, integrity. IPsec framework integrity, making sure that data has not changed in transit. Method of proving data integrity is required. So for example, hashed utilizing hashed message authentication code, HMAC, which is a data integrity algorithm that guarantees the message using a hash value. Two hashing uh, algorithms used with IPsec to guarantee authenticity. So we have MD5, which we've heard before, and SHA. So MD5, Message Digest 5, is a 128-bit shared secret key, and then secured hash program algorithm key, SHA, is a 160-bit secret key. Next, IPsec framework authentication. Two methods of IPsec peer authentication. So we have a pre-shared key, PSK. PSK value is entered into each peer manually. It is easy to configure manually, however, it does not scale well, and it must be configured on each peer. Rivest, Shamir, and Ailman RSA, remember this from looking at our switches, uses digital certificates to authenticate its peers. So remember RSA 2048. So again, each peer must authenticate its opposite peer before tunnel is considered secure. Next, we're moving on to Diffie-Hellman section of the IPsec framework. The DH allows two peers to establish a shared secure key over an insecure channel. Note that DH groups are not supported between multiple vendors at a time. Groups have to be matching and agreed upon. So, say Switch doesn't have group 1 or 5. That means they may have to just share 14 or 15, right? Okay, so there we go. Yeah, so there are variations of groups. So DH groups 1, 2, 5 should no longer be used. 14, 15, 16 uses larger key sizes with 2048 bits, 3072, 4096 bits respectively. DH groups 19, 20, 21, and 24 use respective key sizes of 256, 384, 521, and 2048 bits. Supports elliptical curve cryptography, ECC, reducing time to generate keys. As you can imagine a graph rather than a line, it is like a curve. I don't know what his explanation was that, but essentially faster. Remember that. And yep, I'm done.